Right. So let us start our journey. Morning session will complete the remaining part of yesterday class. That is op-amp basics and amplifier designs we are studying, where we completed all the amplifiers. Just only instrumentation amplifier. At the end, we have one more design we have to do. That is a two-stage op-amp. Yesterday we have been concluded three. Just yesterday we completed the three-stage op-amp, where we got all the ideal characteristics like CMRR is infinite and input impedance is infinite and the voltage gain is high, which is close to infinite, you can say. So that type of amplifier, how to do with the two stages. Just to give you an idea to start our remaining topics today. Very good morning to all of you. So let us complete the final instrumentation amplifier once again. Instrumentational amplifier using two op-amps. This is also a good idea where you can see the size is less compared to previous one. Previously we have used three op-amps where the size is more for you. So to have the less size for you, we'll take two op-amps. So this proposal, how we done? See the design. He has taken here two op-amps like this. This is two op-amps. A1 op-amp, you have minus plus. Plus side I'm giving a potential called VA voltage. And we have here some resistance which is equal to R. And one more R here. This is ground. And it is interconnected with one more R here with op-amp 2 with VB voltage. This is your output. So this is the way I done some design. This is A1 op-amp you can take. This is A2 op-amp. And these two are connected with some contact with a new resistance in the class, that is Rx. For example, for understanding purpose, suppose this answer is given as 1 volt. This answer will be 2 volts. This answer, if I take this as some, you can take some 3K and this you take it as some 1K. This is 1K, this is 1K and this is 1K. So if you clearly observe this design, whatever he has taken to make an ideal amplifier in the class, instrumentation amplifier, the first op-amp, second op-amp, if you clearly observe it, they are looking like two non-inverting amplifiers in the class. So in this analysis, they have taken two non-inverting amplifiers. Whenever you take non-inverting, what is the best advantage from non-inverting technique? If I take the non-inverting technique, the best advantage is wherever you see the input impedance will be infinite. So you get one property directly from this amplifier. Without doing anything, I got infinite property. Because in competitive exams, if you do this all calculations, definitely it will take nearly 10 minutes. Unnecessarily wastage of time for you doing the problem. So first I'll tell you the procedure. You can do it yourself after the class if you want. Just procedure I can tell you. So this is your non-inverting amplifier, which will have a virtual point here, VA. You can apply a virtual point here, and this virtual point, VB, will be here. So you can get two virtual points here, VAB. And this potential, we'll take it as some V01, like this. If you see the current flow, how it will be in this concept, can I say that the current which is coming from A1 op-amp is like this. You are giving some input here, 1 volt, it is giving some output current. The current will divide into two parts here, one side here, one side here. So we have two current flows here. The first current flow is V01 minus VA by R. This is your current. V01 minus VA by R. And this current will be V01 minus VB by R. So these are the two currents which split from the first op-amp. Okay. Sound goes off. Let's take the clicker. Voice is coming or not? Yeah, now it is audible. Advita, great. Show it, now it is audible. You can say. So this is one current and this is one current. And there is one more current here. You can say VA by R. So this current, whenever it comes, it will split into two parts here. One current will go this side, one current will go this side. So it is VA minus VB, VA minus VB divided by some new resistor called Rx. So the above feedback, what I applied again, the resistor should be different. In this application, the below all resistors are same. You can see the class. A resistor should be same always. Only a new resistor which is coupled again feedback, that is a new resistor called Rx. That is the technique of this concept. Okay. Anyway, these are the currents you are seeing. This is one current, this is another current. And when you come here, this current and this current will merge here. So the answer will be VA minus VB by Rx plus V01 minus VB divided by R. So this is the total current we go into the circuit. And finally you will get some response. VB minus this total drop will give the output. It is unnecessarily waste of time to do this all derivations. How we have practiced this from the slide forward, I tell you the trick. It is 2 into, the formula is very simple. 2 into R by Rx. 2 into R by Rx. Here actually the concept here is, whatever the resistors you are seeing here, this resistance has to change. Rx value should be in the formula, should be low value. So you take this as 1K, you take this as 3K. Because the R should be high value inside. That is according to the formula, I understood it. So inside resistors, R value should be high resistors. Above should be low resistor because the formula is conveying here 1 plus R by Rx. Whenever the formula is 1 plus R by Rx, Rx if you have low, you will get more gain. If R will become more, you will get more gain. So our achievement is R should be high in the problem, Rx should be low. In the exams, they will be like this. And another is VB minus VA, we are getting. So this is the formula actually. So why I am telling you it is not required to derive this formula is, it's just looking like non-inverting gain, we got two times here. Non-inverting gain formula is 1 plus R by R. Correct? Here the formula is coming 2 into 1 plus R by Rx. It is just like formula for non-inverting gain. Unnecessarily 10 minutes of time you will waste in gate exams if you want to derive this formula. That's why I have a good practice. 2 into 1 plus R by Rx. By chance if you miss in the exam, what is R, what is Rx? Simply logic is high resistor by low resistor, you just try down in the exam. 2 into 1 plus R by R1. Your Rf is high resistor here. But high resistors will be given in the exam is R value. And Rx will be given low value. So what is the condition for this is, your R should be always greater than Rx. This is the obligation. So whatever the similar resistors we have taken, that is a high resistor will take and Rx will take as low resistor. So I think the problem is very simple. And VA minus VB or VB minus VA difference, doubt difficult, higher minus lower, this will get higher value, this will get lower value. So you can write VB minus VA, like that you can write the difference, because it's a differential amplifier technique applied. So this technique makes me to tell you the gain has been increased again. So output by your VB minus VA is your closed loop gain, differential gain, which is 2 times of 1 plus R by Rx. So you are getting a non-inverting gain, but you are getting double of that gain, which is called high gain, we will say. So we are getting amplified by 2 times. So this is considered to be high gain, which is infinite, you can bring high gain. And high input impedance already we got. And what about CMRR here? What about CMRR? Okay. What is the meaning of CMRR is, if your VA and VB, if I give common inputs, if your output becomes 0, then CMRR is infinite. So if you want CMRR here to be infinite, CMRR, if you want infinite in the class, the only logic here is your output should be 0 for common inputs. How we make output is equal to 0 for common signals? Then you have CMRR is infinite projection. So here common inputs is VB, VA is equal to VB. These are your common inputs. Both inputs should be same. That is called common input. Then if you see the output answer, it is 2 into 1 plus R by Rx into, you are getting 0. It will be 0. So finally I proved that any common input we are applying, the circuit will not allow it to come out. That is called common mode rejection. We have done well. So CMRR will be infinite for this circuit. So we got all the 3 characteristics. It is infinite characteristics, and this is your gain characteristics in the close. So let us make this problem simple like this. Unnecessarily don't waste your time to derive all these things. I will practice in this manner. This is more than enough for this concept. So with this we have been covered 2 instrumentation amplifiers. One instrumentation amplifier is with 3 op amps, one instrumentation amplifier is with 2 op amps. Examiner, if they give this question, don't do blindly the questions. After seeing that you recollect, the circuit is an instrumentation amplifier, the answer is very easy. 2 times of non-inverting gain into difference of voltages, VB minus VA. That will be the answer for it. It will take hardly 10 seconds to write this answer in the exam point of view. If you have the clarity like this in the formula. It is 2 into 1 plus R by R1. Here R became R value and R1 became your Rx value in the problem. So this completes my yesterday class. Whatever the topic remained, we have been covered. Just close this matter. We'll come to today class. Only 4 parameters are remaining, which are called special parameters I said in the class. One is CMRR calculations. I'll explain you. Why these people are telling CMRR is infinite for V not equal to 0 case. That I'll explain in the class. And second calculation part is offset, one of the typical analysis. After completing of that, sleeve rate is there, and finally empty. These 4 topics, if you can cover today, we can start practicing the workbook. That is our today job. By afternoon, if you complete all these issues, afternoon we will start a new module called as mathematical operations in the afternoon class. Okay. Today we are having a journey like this concepts. So let us complete it. If anybody is interested to prove this one, take some white paper and take this total current equations and just make a calculations by yourself. And let us see that whether the proof is correct or not. You can just by yourself. Hardly it's a KCL mathematics. Okay, you do some mathematics. All the current relations are given in the board. You do it yourself and just prove that whether the answer is correct or not. That you do it at a paper. Okay, notes make is not required. Notes derivation is not required. Straightforward, you can copy the formula there. Because the formula is very easy. That's why I'm not derived anything there. So 2 into 1 plus R by R1 here. Your R became R here. Identical resistors. They're all identical in the exam. And this is a new resistor called Rx value. So this completes my today class on amplifier design. Part is completed. The first we have studied inverting amplifier, we have studied. And next we have gone to non-inverting amplifier. After that we have seen the voltage follower design. Next we have seen the phase shifters. After that inverting amplifier with the T-network techniques. Next to non-inverting amplifier with the T-network. After that differential amplifier. Lastly we covered the instrumentation amplifiers. Who will study like this? Subject looks easier for him. Okay? This is the order of study for you. So if you complete this one, please tell me. It's a very simple diagram and simple formula. Right here, CMRR is infinite means output should be 0. What is the meaning of that? If anybody gives some common input to the op amp, it is common input means what? Same input. If output becomes 0, what is the meaning of that? Your common input is rejected. That is the meaning or not? In the assumptions going here, the definition of what you said is common mode has to reject. As it is rejected, you are giving 2 inputs same there. PA is equal to VB is a common input for both the systems. Then output became 0 is the meaning for CMRR is infinite. Okay, suppose output is not 0. You got some non-zero quantity. Then CMRR is not completely rejected. If output is completely 0 directly in the class, you can say CMRR became infinite. Complete common mode rejection happened. That is the simple meaning here. The name itself is telling CMRR, common mode has to reject. Yes, it rejected. Your output is 0 with your common input. That's why it is called CMRR equal to infinite. And you want better knowledge, I'll explain in the next topic about CMRR. Really how to calculate for this equation I'll explain. Okay? So let us keep a beautiful topics now. Each topic is a very interesting topic and individual topics there for competitive exams. Let us write a neat analysis on these topics. Okay? So exactly 1 in the 4 time is there. We'll finish the scores. So let us start with the first topic in the class. Let us start with the first topic today. Let us start with first topic. That is called special characteristics are the special characteristics of op amps. Special characteristics of op amp. You can keep the heading like this. There are special characteristics of op amp. Special characteristics of op amps. In that the first topic is topic 1. We have is CMRR is the story. CMRR. This concept how to explain and how to calculate in exam point of view. Generally CMRR whenever they ask in exams, they'll give CMRR circuit by differential amplifiers because inverting non-inverting we cannot solve because CMRR is a word comes when you have 2 inputs for the amplifier. So CMRR generally will be calculated only for differential amplifier. You should have the common sense on this. Differential amplifier. So nobody will ask you calculate CMRR for inverting non-inverting. It will ask only for differential amplifier. Suppose I take an example for this differential amplifier. I'm taking like this to study this concept. This is minus plus. Suppose if I take this as R1 and we have this as R2. This is R2 and this is again R1 I have taken identical. This is R2. You have this is V1 voltage. This is V2. Yesterday class, this is a subtopic which you have taken in instrumentation differential amplifier using 3 op amps. And I said directly in the class that your CMRR is infinite. But how CMRR is infinite, we have to do the analysis today. Okay. Now I'll prove that CMRR will be infinite for the circuit. For that, how to do the analysis. In exams, they'll get a question like this. They'll ask you, please calculate CMRR. Sometimes they may take these resistors different. At the time, CMRR cannot be infinite. You'll make it some quantity. But in this class, you'll get infinite. What is the reason is, you have taken some identical structure here. Above R1, R2, same resistors you have taken below. Maybe we have some balancing here. CMRR definitely will become infinite in this case. So how circuit means simple logic. By seeing the circuit, if I take this answer as simply V plus. Okay. Can I use superposition theorem? I'm using superposition theorem. Superposition I have used to find out my output. So why can't you do directly the analysis without doing step by step? First, a non-inverting answer I'm writing. It is 1 plus R2 by R1. This is the non-inverting gain. Into input should be, your non-inverting input is V plus. This is my first answer called non-inverting output. 1 plus R2 by R1 into V plus. V plus will be the input for the op amp for non-inverting. Plus inverting stage is minus R2 divided by R1 into V2. This is the second input. So the only difference between non-inverting and inverting is non-inverting will take directly at plus point, but inverting will not take it V minus, will take it V2 position. That is the difference between inverting and non-inverting or inputs. Okay. Now the point is, what is V plus here? It's a voltage division rule. So LCM, if you take this as R1 plus R2 by R1, you can take this as an LCM. V plus can be written as R2 by R1 plus R2 into V1. This is a voltage division rule applied in this network. Plus minus R2 by R1 into V. Because of selecting the symmetrical resistors here, you can see that there is an advantage of cancelling these two resistors. He has done some balancing there. R1 plus R2, R1 plus R2 will be cancelled in the formula. And finally, you got a component here, R2 by R1. R2 by R1 into V1 minus R2 by R1 into V2. So like this, you got the output in the class. Okay, both sides, you have the gains are equal we are getting. So V1 ka gain and V2 ka gain we are getting same. One is with a positive gain, one is with a negative gain. Whenever you can make like this, we can call this as A1 gain and this as A2 gain, we can define in the class. So we can write this answer as V0 is equal to A1 V1 plus A2 V2. So you can write like this, your equation for differential amplifiers. One is A1 is nothing but your non-inverting gain here. Your non-inverting gain. We got it as R2 by R1, I defined as A1, non-inverting gain. And A2 we defined as inverting gain. Inverting gain, we got it as an A2 gain, which is minus R2 by R1. But both gains are looking same. According to this design, both gains are coming same. But one is a positive gain, one is a negative gain, we are getting the plus. Okay? Vishal here, Vishal is asking why V2 not take V minus. Common sense use karo idhar. मैं क्या बोल रहा हूँ? V minus is a virtual ground. Yesterday class V minus is equal to V plus. Then how can you write V minus and V2 are same? It's a negative feedback here. कल class basics बताया. If you forget the basics, there is no meaning to take this class. V minus is not equal to the input of your inverting system because the current will flow from input to the feedback. That is the reason your V minus and Vn will not be same. That's why here V2 we have to write, not the V minus. Okay? The basics are very important from yesterday class. Whatever I thought, the basics have to apply clearly here. So don't write V minus here. You'll be failure in class because if you write here V minus is equal to V plus according to virtual ground. So virtual short and virtual ground both are same. But here these two inputs are different. V plus is different and V2 is different. So don't be careful about these points. So A1 is non-inverting gain, A2 is inverting gain. Up to here if it is clear, but I got the gains of A1, A2, but CMRR definition is not A1, A2 definition. CMRR if you want to calculate, it is AD by AC is CMRR. That means CMRR if you want to calculate, we don't need non-inverting gain and inverting gain. We want a differential gain and common mode gain in the class. Then how to bring a differential gain from your inverting non-inverting gains? That is the logic. In first classes I taught you differential amplifier. In differential amplifier, how to define your inputs inside the amplifier is your V1 will become VD by 2 plus VC. And V2 is equal to minus VD by 2 plus VC. This is the knowledge we talk about V1, V2 inside the differential amplifier. Externally you are giving V1, V2, but inside when they go, they try to divide into two parts which we study in differential amplifiers. So who has the type of good knowledge, differential knowledge? These are things are easier for you and you can solve it very comfortable. So now onwards V1 is a non-inverting input which will go inside the op amp and it will divide into two parts. One is a common mode, one is a differential mode. This practice we done in a good manner I am expecting. Okay? If you substitute these formulas in the original output, it becomes A1 into VD by 2 plus VC plus A2 into minus VD by 2 plus VC. So converting your parameters into VD VCs. If you convert these parameters into VD VC forms, okay, then you can see the common terms. A1 minus A2 by 2 is one term into VD plus A1 plus A2 into VC. So the style of your output I change it like this inside the op amp. So who is writing like this, who is writing like this is same. Here you have written A1 V1, when it goes to the inside the op amp, I change it to AD VD form. That means if we get VD here, this form you can write it as AD. I define my formula AD like this. This is the knowledge which we want to solve the problems. And this formula VC wise, there will be a gain called AC. So this is my work behind the concept. So anybody asks you what is AD/AC, they'll come from a non-inverting and inverting gains only. So what is AD here is where AD, which is called differential gain. The formula is very important. A1 minus A2 by is the formula. Non-inverting gain minus inverting gain by 2 is called as your differential gain in electronics. So like this you can prove the AD formula. In the similar way, you can solve for AC also. What is AC you can define in the class is AC is equal to A1 plus A2, which is called common mode gain. Common mode gain is defined as non-inverting gain plus inverting gain. We call this common mode gain in the class. So these two formulas are valuable for calculating the subject of CMRR calculations. This one formula and this is one formula we should not forget in the classes. common mode and differential mode how to bring from the equations. So A1 minus A2 by 2 we call it as AD, A1 plus A2 we call it as AC, your amplifier circuit. So then what is CMRR here is, CMRR is nothing but AD by AC, which is A1 minus A2 by 2 divided by A1 plus A2. This is CMRR calculations. A1 minus A2 by 2 is AD formula divided by A1 plus A2. We are going to solve it in exams. Okay. First, a student job is to calculate these two answers first. A1 A2 को first solve करो by using superposition theorem. Bring that A1 one side, A2 one side. After that, doing this job is not a big task. A1 minus A2 by 2 will give the AD. A1 plus A2 will give the AC. But I said that this circuit has CMRR is equal to infinite. What is the reason for that is, here A1 minus A2 by 2 is a differential gain. Keep it like that. But have you seen common mode gain is an addition of two gains. This two gains addition. But one gain, other gain have same gain with a negative sign. So I think your gain R1 by R2 by R1 minus R2 by R1. So this quantity will become AD by 0. This will become infinite. So like this I proved that CMRR will be infinite for this circuit. So this much of good knowledge is very important to solve CMRR questions. Very easy. Formulas are very easy. Only thing is investigation. V1 we have written VD by 2 plus VC in the formula superposition theorem equation, and VC we have written as V1 plus VD by 2. That is your, these two formulas should come into your logic. One time if you get that logic, you can bring your AD and AS very easily. So AD formula now one would say is non-inverting gain minus inverting gain by 2 is your AD from your amplifier circuit, and AC is nothing but non-inverting gain plus inverting gain. That will finish this type of questions. All the times they may not give differential amplifier circuit with symmetrical resistors, they may give irregular resistors. At that time you may get some quantity there CMRR. But in this class, to prove that this circuit has CMRR infinite, I have taken particularly this example to show that for a student why CMRR is infinite. The only logic here is if the two gains come same in the design, A1 A2 if it gets same with the one has a negative sign, one has positive sign, then CMRR is infinite because common mode will become 0. A1 plus A2 is the gain for it. So this is the trick of first calculation called CMRR. So first concept is completed for gate type of questions. Very beautiful concept. One special topic I covered, CMRR how to calculate. That knowledge is completed. CMRR how to calculate. These are the procedure and steps how to find out the CMRR. So please make a hobby about these two formulas. Okay? Two formulas are very easy. AD is nothing but non-inverting gain minus inverting gain by 2. And AC is nothing but non-inverting gain plus inverting gain. So please complete up here. I take some water. So Sharmidas, your doubt is okay, simple doubt only. 1 plus RF by 1 is non-inverting gain I said. But if you change the structure of the amplifier with the non-inverting systems, I can change the non-inverting formulas also. I have changed the formula by taking some R1 and R2 branches. So always remember the V1 before, whatever the answer you will get, you take it as non-inverting gain. Because previously we have not designed like this. We have taken R1, R2 extra, which can change your gain. So you should not blindly remember that formula 1 plus R by R1. That is correct only, that formula, when there is no R1, R2 resistors. Only if you have R1 resistor, at that time that formula will be valid. If R1, R2 you have taken extra, then the formula will change automatically. So you have to convey that V1 before whatever you have, that will become your non-inverting gain in this design. Okay? Sometimes you may get 1 plus R by R1, sometimes you may not get, because the design have changed, structure I changed, then how can you expect always 1 plus R by R1 formula? Okay? You should have the type of thinking always. Sir has been changed the structure here. Not only R1 he kept R2 also, so voltage division rule is coming here. Because of voltage division rule, the formula slightly varies. Okay? So that is the story how we applied. Because ultimately, CMRR infinite chahiye mere ko. If you write 1 plus R by R1 design suppose, it will not cancel, CMRR will not become infinite. To do that, this is the modification I have done in differential amplifier techniques. Okay? When R2 is not there, then you will get 1 plus R2 by R1. But the structure is different, the design I made. So let us move to a typical topic today, which is called offset, is the next topic. Offset thoda time lagte humko, offset the calculations will be complete. Sleeve rate is easier and FT is easier to complete. So let us understand the offset formulas, how to apply for the questions. So what is the meaning of offset? Because in the next classes every time I use the word offset, okay, for my non-linear applications, like positive feedback or open loop, offset we are not controlling. Only for negative feedback we have to control it. So how to do this controlling? First of all, if you know how to calculate, then we can understand how to control it. So let us see how to understand the offset conditions. So can I expect that this topic is clear and completed? So if it is completed, please write down the message completed, sir, and we understood, sir, so that I'll go for the offset knowledge, which is a very important topic for your gate type of questions. Okay? So Ujjwal Kumar said completed. What about the other students? Roy, very good, completed, great. So remaining students, can I expect completed? Great. Kamlesh, yes sir, great. Yes, clear and understood, great. Samresh, wonderful here. If you have been understood this topic very clearly, we'll go to the next topic called offset calculations. Okay? Offset calculations, we'll try to understand. The next topic is second one. Keep the heading. Second one is offset we call. Formulas are very easy, just a procedure you have to understand. Offset. In brackets you can write what is the meaning of offset in op-amp is. Unwanted input is called as offset in op-amps. Unwanted input. So how many unwanted inputs will come in an op-amp? If this is op-amp, somebody has designed suppose minus, plus, this is your output. For example, negative side and positive side, I am not given any input, so no signal is given. But it is being biased with VCC and it is biased with minus VE. So I'm doing some experiment in the lab that without giving any input, okay, is there any output will come? Just I have been done the experiment, and I've seen that every op-amp is giving output without giving input. So then the designer said, I done some mistakes in my designs. There will be some mismatchings will be there. All these troubles created me to create some inputs in the op-amp. Whenever you apply DC power supply, automatically some inputs will generate inside the circuit. We call DC offsets. What is the DC offset? Our designer has given 3 types of errors inside the op-amp. There are 3 errors will create. One error is called VI0 error. This is one error. Another error can create here. That is II0. This is another error. Designer is telling current-wise 2 errors will be there. Another error is I bias. So this person is telling 3 errors will come when DC supply is applied to the op-amp. Okay, when DC supply is applied to the op-amp, automatically it will activate and it will create some inputs like this. 3 different inputs we are seeing in the board. So today clearly we'll understand when DC supply is on, why these are coming. That issue I'm going to talk in the class. So first of all, what is VI0, what is I0, what is I bias? I'll teach you afterwards. First see the diagram inside differential amplifier. We have our transistors like this. Inside I'm observing my first stage op-amp. First stage op-amp block is differential amplifier. So what is going to happen in a differential amplifier? You can see. This is your 2 inputs which are grounded. Bottom side we have RE and battery is minus VE. Battery is minus VE. Top side we have RC and it is being commonly connected with single supply VCC at the top. So we have dual supply lines. Inside these batteries are on. When these batteries are on, what he's telling is, theoretically you are telling Q1, Q2 are identical and you are teaching the classes. But designer is telling he knows the real fact that in IC designs Q1, Q2 cannot be identical in nature because no 2 things will be identical in nature. Nobody can create. There will be small mismatch. Okay. So there are 2 issues are going. Theoretical theory is telling that this theory is telling that Q1 and Q2 are identical. This is theoretical theory we can say. But practical theory, realistic theory is practical. If you go for a practical vision, that is designer is telling that I have never seen Q1 Q2 identical. Q1 and Q2 are in mismatch. This is the story going on. One person has done theoretical, one person has done practical. First person will do theoretically, then he'll go to the practical designs. Practically, theoretically, not matching. Okay? Theoretical person is telling, okay, so whenever you apply here ground and battery here, we have a diode in DC analysis. And we have a diode here also, 2 base emitter junction diodes. I said in the class that the 2 transistors will get on by minus VE battery biasing. Because of higher potential, lower potential, these 2 will get on by, this has VBE, base emitter voltage, and this also gets on by VBE, base emitter voltage. So yesterday class I told you that both will have VBE in the class, and both will have base currents equal, IB and IB. This is called a theoretical mind in the subject. A person who is theoretical person, he'll teach like this the class that base currents will go same because both are identical, base voltage will be same because both are identical. This is called theoretical vision. But when the person comes to realistic or practical vision, you said that Q1, Q2 are in mismatch. Both transistors betas are slightly varying each other. If one beta is 500, the other beta is 510 suppose. There is a mismatch between 2 transistors. That is called mismatch. When there is a mismatch, automatically the person has to talk like this. This IB1 will come. This is IB2. This is VB1. This is VB2. That means your input parameters are mismatching. This is the common sense word the subject. So realistic sense is different. Theoretical sense is different. So what we think theoretically, it cannot happen in realistic manner practically. That is the vision. Small errors will be there. So you can see that because of mismatch, the base currents are slightly different. And the voltage is also slightly different in the class. Now what I'll do is, assume that, for example, this input, whatever you're seeing, is a non-inverting input. We'll take it. And then define suppose here, this is an inverting input. We'll take one is inverting, one is non-inverting. So we are taking as indication that this is a non-inverting, that is an inverting. So this plus indicates non-inverting suppose. The designer decided that this is a non-inverting input. Terminal. And he decided that this is an inverting input. And it has given to the user inverting input. For example, he defined these 2 things. One is non-inverting, one is inverting. Inverting, non-inverting, we are not given any input. But there is a current going here because of my biasing. Because of DC biasing we are getting. Now I'll give some names for this. This IB1, now onwards I'll call it as I plus I call. I plus is nothing but some current has been generated inside the op-amp in the non-inverting side. That is called base current of your transistor, which I indicate as I plus. And IB2 is the current is generated by DC biasing circuit by I minus current we can say. So these are called as inverting, non-inverting currents, which I define in the subject. And VB1 is voltage, we'll take it as V plus, because this is the voltage generated at non-inverting side. And this is the voltage generated at inverting side. So this is the story of your concept. Now the designer started to explain what are the inputs have been generated means. Voltage wise also we are getting difference, current wise also we are getting difference. The terms only he has written in the board. One is VI0, one is I0. One is voltage difference, one is current difference. So we can write here simply I can define the points like this. First point, VI0, we call it as input, now one words, it is called input offset voltage we can call. Input offset voltage, we call it as VI0. This VI0 can be positive, can be negative, कोई भी हो सकते हैं. Because V plus can be more than V minus, or V minus can be more than. That's why we generally teach with the magnitude. V plus minus V minus. Because VI0 can be positive, can be negative, कोई भी हो सकते हैं. Okay, that will be explained by the designer saying that my offset is negative sometimes, my offset will be positive sometimes in the op-amps. Because nobody can tell, as a user I cannot tell this is more, that is more. Who has been created it inside the design, he knows that V minus is more than V plus, or V plus is more than V minus. So until unless nobody will ask you science, you can take it as magnitude is better. So V plus minus V minus, the difference we call it as now one words, input offset voltage is created already because of this difference. Typically how much this value is? Typically it vary between 1 millivolt to 10 millivolts. This much mismatching is coming. The difference will change between 1 millivolt to 10 millivolts, which is an error for your VS0. Coming to the next one, 2 more errors I'm defining, seeing the board. The second error we call it as IS0. Second error is IS0. IS0 means input offset current. Input offset current. Input offset current. IS0 will be same like I plus minus I minus. Keep it in magnitude because IS0 also same story. It can be positive or it can be negative. That's why in magnitude you keep that offset. So this is the current difference, this is the voltage difference. Up to here I think nobody had doubt in the class. It's very easy and understandable. The last point, what is the next point we have is point number 3. The last point I'm taking. Generally if the current enters I plus and I minus, what will happen? You will have some I plus value as the current will divide as I plus minus I minus by 2 plus it will divide into 2 parts again. Current also will divide into 2 parts. I plus I minus by 2. So this is about I plus. Nothing is there. As the voltage divides like that, VD by 2 plus VC, current also will be the same style. It will also divide into common mode, it will divide into differential mode. So this is the structure we can see. So this formula, I'm calling it as I plus minus I minus is IS0 will take divided by 2 plus I plus can be written as IS0 by 2 we can write. And what is this I plus I minus by 2 is? We call this as I bias current. So you will get I plus like this. So I think not only IS0, we are getting some more error called bias current error. Bias is nothing but common mode current. That common mode current we call technically as I bias current, which is I plus I minus by 2. So this is an extra error is coming in the class. Because of differential amplifier, it will divide into 2 parts. That is the main reason. One is a differential, one is a common mode. Common mode here is I bias current we say. That is also an error for you. So what is I minus if you want? It is I minus I plus divided by 2 plus I plus I minus divided by 2, which will be minus IS0 by 2 plus I bias. So individually if you want to solve what is I minus and I plus, these are my definitions. So what is the last error I can define from this mathematics? What is the last error is I bias means what? According to the board. According to the board, what is the meaning of I bias? So where I bias is nothing but bias current. Bias current we call, which is nothing but I plus I minus by 2. This is called bias current. I bias current is completed. So these are the very interesting formulas actually to do the questions in basic knowledge called offset currents and voltages. So finally by seeing this, a student should understand in any op-amp design when you are creating DC biasing, 3 errors will create always. One is a voltage error, 2 are current errors. Voltage error is here, V1 minus V2 by, there is a only difference we'll see. But what about common mode voltage means? I already rejected by using your CMRR circuit. Common mode rejection circuit has been cancelled that one. Only we have here first error, VS0 error. Common mode error voltage will be cancelled by the circuit. But here current wise it cannot cancel. That's why current wise we get common error, not only the differential error, but the voltage wise we get only differential error, differential voltage, but we will not get the common. Common value will be rejected by CMRR circuits, which we design in the classes. So these are the 3 errors we are seeing in the class. So I think we should never forget these errors. Typically if you want this analysis, typically this range will be around some 10 nanoamperes you can take. And this typical range is, 100 nanoamperes you take. The errors of currents are very small. Okay. In terms of nanoamperes we are getting. And in exam if anybody asks you, difference current will be more or bias current will be more means bias current will be 10 times more actually. So bias currents are more serious compared to offset current. Difference current is less actually, average current is more. That's why this compensation is very important today class called I bias compensation we have to do. For that what is the trick and what is the analysis behind that? Let us see one by one stories. So how to compensate this bias current because it's getting more error compared to offset current. So this completes my today class. So let us have 3 formulas I'll create now. If the question is being asked, can you calculate output offset in an amplifier using VA0 error? Separately they'll ask you 3 different errors. VA0 wise, how to find out the output error. There is a one calculation. Second one is IS0 wise, how to calculate. And I bias wise, how to calculate. 3 steps, 3 formulas I have to create. Let us see how to remember and how to keep in mind these calculations. Let us understand it. So now we have 3 case studies now. Till now just I define what is offset currents and what is offset voltages. So I think now onwards the student should not ask me, sir, offset the meaning guy. Okay? Don't be like okay? Be like an intelligent fellow. Offset reality is this one in the board. Unwanted things will create automatically when DC circuit is on in an op-amp. Okay? 3 unwanted things. So one is VA0, one is IS0, and one more is I bias. 3 errors will create. So nicely write down up to here so that I can start the 3 case studies to complete this task now. Okay? Examiner, so many times these questions came. VA0 is how to solve it. Who knows the trick, he will do it. There is not a big analysis. But one time trick malum nahi hai, he cannot do the question. There is a problem with these concepts. So that's why I want to tell you trick concepts now. VA0 when they give in the exams, how I solve my problem, I have to show you the trick for that. So if it is clear, please tell me clear up to here. So that I can proceed to the 3 steps now. Like a problem we'll do it, then we'll understand how these questions can be done. Okay? Yes, Ghosh, this is 100 nanoamperes. This is 100 nanoamperes, this is 10 nanoamperes. Okay? IS0 is 10 nanoamperes, I bias is 100 nanoamperes as well. If you go for MOSFETs, it will come in picoamperes. They are all BJT typical values. Okay? That means MOSFET will have more matching compared to BJT. Because BJT is complicated, it will have mismatchings more. That's why nanoamperes, but MOSFET will have picoamperes. You'll get more. That's the reason most of the times I see MOSFETs in the design part. Samnidas here, VA0 is not rejected. CMRR is not rejecting VA0. It is rejecting V bias. V bias communicating. It is rejecting this word, V bias. It is V1 plus V2 by 2. This is rejected. So common mode voltage is rejected. From the previous derivation what you learned then, CMRR is equal to infinite we got. For what means common mode inputs will be rejected. That's why here we are not studying about the error due to V1 plus V2 by 2. Because the circuit itself will reject that. So there is no trouble with V bias. But there is a trouble with I bias, not V bias. Okay? So here tamko leave the circuit because previous design, whatever you design CMRR circuit, it can just block it. This error. So no need of talking about V bias in the class. So into three parts. So case 1, case 2, case 3. I'll explain you three cases now. Case 1. Case 1. So we are interested to calculate V out offset. I want to calculate V out offset due to only Vi0 error. Actually, we have three errors in op-amps, but at a time three errors we cannot solve. That's why we give some condition here. Whenever I'm solving this one, V out offset due to Vi0, we'll give some condition here. What is the condition here is? Condition here is I0, you treat it as 0, and I bias, you treat it as 0. That means we are not thinking about current errors, we are thinking about voltage error. So this is one condition you keep to start the derivation. I bias, you have to make it 0, and I0 should be 0, so that we can talk only individually about V, I0 error. In the exams, they'll use some data for you, like this. So they'll give one amplifier system for you. This is your amplifier. Plus is ground. This is your output. We have feedback. This is R1, this is RF, and this is ground. They'll give a circuit like this. And suppose this is 1K and this is 9K. These are my values. Can you see that this structure is called an amplifier structure? But this amplifier, in further classes, we can make inverting, we can make non-inverting, we can make differential amplifier. But first of all, what he's asking is, can you tell me your error inside the amplifier? How much? First you calculate your error, so that we'll try to use some technique to cancel that error. So user has to calculate first how much error is coming from your input error given by the designer. Okay, designer will use an error for you. How will measure the output error from this amplifier? Given Vi0 error is for this 10 millivolts. Designer said for this op-amp, it is 10 millivolts. Now the concept is, this input, if I apply here, suppose, at the plus side I applied that voltage, it will become non-inverting amplifier because all the output offset aa jayega. Suppose this input I kept at the inverting side, okay, that will become inverting gain into your input, into the output. So where to apply that input, that is a doubt. Shall I apply this input to the plus side or minus side? That is the confusion I'm getting. So to avoid that confusion, yesterday we learned some trick for that. That trick wise I'm teaching. See here. Different ways we can teach, but trick wise it is easy to remember. Yesterday class, in inverting amplifier, can you recollect? What is your gain? Practical gain you got, AF. If you observe that formula, it is minus RF by R1. Realistic gain is not this one. We got some extra error here. 1 plus 1 by AD times 1 plus RF by R1. Like I hope you remember this structure. This is the error we got yesterday. Error is due to this one. This is the error. So another formula, if you observe, non-inverting amplifier. Non-inverting amplifier. Here also if you see how the error is coming for non-inverting is, AF is equal to 1 plus RF by R1 divided by 1 plus 1 by AD into 1 plus RF by R1. So this is your formulas. Okay, in this what is my observation here is, which gain is coming error here? If you observe correctly, this is the error for you. This gain is the error we got. 1 plus RF by R1. Here also the error is coming due to 1 plus RF by R1. That means error is coming due to non-inverting or inverting gain. Means it is coming due to non-inverting. So you can think that error always comes from non-inverting terminal. This is the point first you have to learn. Because this error is due to non-inverting gain. This is non-inverting gain error. We are not getting inverting gain error. Here also we are getting error due to non-inverting. So this trick is enough to finish the problem. Non-inverting gain. So errors always come from non-inverting, he said. It is not coming due to inverting. Thus, if you want to reject that V bias error, we have only one special technique called differential amplifier. A circuits will not avoid it. You have to go for a differential amplifier circuit such that it can reject that one. Otherwise, for a single input, we should not talk V bias error. Because for single inputs, we never talk about CMRR calculations. CMRR is a word comes only when you are doing differential amplifiers. But I0, I bias, Vi0, they all things are common errors, comes for every amplifier. But V bias is an error which we can cancel only in differential amplifier in electronics. Okay? There's a special case which we are talking. The remaining errors are common errors for everywhere in the op-amp amplifiers. So that point please try to understand it. सबने दस आपके लिए explain किया. अब generally doubts ज़्यादा पूछ रहे हो देख सकते हैं. थोड़ा logic understand करो. Okay? CMRR is a word comes only for common mode voltage reject करने के लिए. We have only one topic called differential amplifier. In other topics we should not talk about V bias error. Okay? Because we are not bothered about V bias error. In other case we cannot solve it. But only in differential amplifier we can kill it. That's why we talk about differential error. V bias is cancelled. Okay? The remaining errors are common errors. Everywhere it will come. That's why we are studying it. Input error, inverting amplifier will get Vi0 there. Non-inverting it will come. A basic op-amp will have these errors. This is the way first we are studying the concepts. So don't talk about V bias here. Only three errors you talk always. So error always come from non-inverting terminal understood from these structures. Then I think now it's easy for me to finish this problem. What you do in the exam is simply minus plus whatever the error given in the problem, that is your offset voltage, you just keep to the non-inverting side. To find out the error, he said that suggestion, don't give that input to the inverting side, give to the non-inverting because previous formulas are telling the error will come from non-inverting technique. This technique is enough to finish the problems. So we have here, this is output, this is RF, which is 9K, and this is R1, this is 1K. I think who knows how to hear the trick? Error always come from non-inverting. This logic, who knows? I think doing this question is nothing for the student. The only trick he must know, input where to give. Error, whatever you have given input where to give, non-inverting side is set. Because there is some reason for that. So I think problem is completed. So doing offset questions are very easy, but you must know the logic. Why we are applying, for where you have to apply. So the problem is completed. This is given 10 millivolts. So output will be, formula will be, V0 is 1 plus RF by R1 into Vi0. This is the formula for V out offset. So this is the first question. How are we doing the subjects? 1 plus RF by R1 into Vi0. In the labs we are going to calculate the answer with this formula. It is 1 plus 9K by 1K into Vi0 is 10 millivolts. So it is 10 into 10. It will become 100 millivolts. So like this I'll finish the offset error. So with this case 1 is completed in the class. First case I completed. VS0 errors, how to solve means it's a very simple formula. Non-inverting gain is your error into your input will give the output error. So never give the input to the inverting side. Always give the input to the non-inverting side. So this completes my first 1 mark question for you. Let's see other 2 1 mark questions how to solve in competitive exams. Sometimes they'll give I bias no error. How to solve I bias error? We'll see second step. We'll control that error, then we'll come to the offset current error. So if anybody asks me this error, sir, how you do it, try to neglect it. Means I already told you there is a 1 and 5th pin, we call it as offset null points. Because of this null positions, what we do is we'll give some potentiometers to VC supply and minus VA supply. We'll just adjust the batteries. Externally, when you adjust the DC batteries, inside the difference in voltages will adjust, and finally they will become 0. So the best technique we use is instrument technique we use called potentiometers. We'll use potentiometer technique we are using. So we are using potentiometer technique. So we use some potentiometer adjustments there in the labs by using that instrument. We can just set the value to 0. Externally, if we change the battery slightly, inside the voltage will change. Then automatically we'll adjust in such a manner the output has become 0. So that is one technique called potentiometer techniques we can apply. So here we are not using any circuit compensation. That instrument device we are compensating it. So PA0 technique, potentiometer technique. So let us see the second concept. The second biggest error I have seen is not IS0. We have seen is I bias is the next biggest error. So let us complete the second error how to calculate. Error number 2 we'll try to see. Second error. So up to here I think this is not creating any problem for you. This concept is very simple. You can solve it in exams, no worries. Only the trick you must know in the class is where to view the error, which is non-inverting will be the error. The secret you have to understand by this background formulas what we derived in the class. So let us see the next concept. That is I bias error, how to solve it. Let us understand it. It's a very complicated topic, but simple to analyze the subject. Offset is one of the typical concepts actually. But really I am expecting in my class you are understanding well this topic. Yeah, show it set completed. What about the remaining students? I'm waiting for the students to complete it. So Ujjwal is also completed. Great. Yeah, Akash Mishra, Kamlesh, Shankar. Who is this? Shivrat Radha. Ghosh completed, Roy completed. Great. Samresh. Kalda. Saudinya. Very good. You have been completed it. Let us go for the next issue here. Step 2 we'll see case 2 concept. In case 2, whenever you go to case 2 analysis, we are trying to develop the concept of V out offset. Due to I bias, how to solve is the next calculation. Let us see the problem, how to solve with I bias. What is the condition you have to keep in mind when I do this problem is condition. Condition is Vi0 should be 0 and Ii0 should be 0. This is the condition. Whenever you said the word Ii0 is equal to 0, what will happen? Let us understand it. So there is a concept called I bias in the class. What is I bias? I said in the class is I plus I minus by 2. This is called average of your two currents is common mode current, I bias current. But Ii0 you said 0. When Ii0 is 0, it is I plus minus I minus is your Ii0, which you made it as 0. Then we can take a principle here. I plus is equal to I minus. These conditions we can use for this problem. It's called I bias techniques. Yeah, Rahman, actually this potentiometers we are adjusting to one of your supplies. VCC or minus VE, we have to apply one. Therefore, 1 is a terminal or 5 is a terminal. These are two connections or two potentiometer techniques. If VCC is connected, we'll go for one terminal, that is called 1. Otherwise, if you go to 5th terminal, that will become another null point. Anywhere you can just make the null. So if you want 1, you can null from there. If you want 5, you can null from that. Okay, any one case you can do it. Don't change both the batteries at a time. You just connect to one battery, the potentiometer. It may be plus VCC or it may be minus VE. Okay, Rahman? That's the meaning actually. So I plus is equal to I minus. This technique we can use. Therefore, I bias current, what happens with this condition is, it will become I plus I minus will become I plus by 2. Otherwise, I minus plus I minus by 2. We can write like this. So I plus by 2 will become I plus is equal to I minus. So in my derivations, whenever I see I minus or I plus individually, I call it as I bias current in the problems now. This is a background mathematics first you have to develop. So I bias can be written as I plus or I minus according to this issue. So now, if you see the diagram, this is your op amp. Minus side, we have some current here, which is I minus. And plus side, we have some current here, which is I plus current, which are generated inside the op amp. This is your output. We have ground here. We have the amplifier here. This is R1. This is ground. We have a feedback here. So this is RF. So like this you are seeing the model. Inside we have two currents, I minus current and I plus current. So whatever the I plus current you are seeing here, the same current will start to flow from ground to this transistors inside. So same current will go I plus. So this I minus is not 0. Some current is there you are telling. So can I take a virtual ground point? This is 0 volts. So this will become 0 according to the virtual ground point. This is ground here. This is 0. So no current will be there here. In between ground to 0 volts, there will be no current. Now some current will come outside this current. The same current will go back. Due to the excitation of I plus current, we will get some current out. So that current, whatever you are getting here, will go back to the feedback. How much this current means? If I apply KCL here, it is not more than I minus current. The same current is going to I minus because no current is this side branch. This is a very simple way of analyzing the offset current inside the diagram. Okay, I minus current is going. Now what is your output here? Means this voltage plus this voltage drop. So V output can be written as I minus into RF plus 0. This is your output. I minus into bias you said. So we can write here I bias into RF. So I think I've seen the formula is ready for output offset. The formula is completed. So whenever you want to solve this bias current problems, you require here not R1 resistor, we require here RF resistor. You already know that RF is a high resistance. It can be 100K to 1 mega ohm, we can keep in the exams. So if it is kept to very high resistance, the resistance into the bias current, if you multiply, the output error is coming more. Because it's not R1, it is RF resistance. That's why the error is coming more. For example, we'll take this as highest resistance is 1 mega ohm suppose. Highest resistance we can keep 1 mega ohm. So I bias current in the problem given is, we'll take I bias is suppose 100 nanoamperes. 100 nanoamps, we'll take. Okay? If I bias is 100 nanoamperes, then what will be the V naught offset? It is 100 nanoamperes into 1 mega ohm. It will become 100 millivolts. You can see the error, whatever you are expecting here, is coming same like your VS0 error. But VS0 have 10 millivolts input actually. But here you have 100 nanoamperes. Current is very small. But error is coming just like VS0 error. So what is the main problem is, not due to this, due to RF we are getting error more. So RF is creating the problem in the design. Because of very high resistance we can take up to 1 mega ohm, that will get more and more error for you in the subject. So this is called the most typical error coming in the class. But this error, nobody can use potentiometers to solve it because potentiometers adjustments we can do only for difference quantities, not for the common quantities. So how to cancel this current is the main issue came in designing. This has to be done by the circuit itself. Okay, you have to keep some extra component inside the op amp such that your output has to become zero and the error should get cancelled. That beautiful technique today class is I bias compensation technique. In gate exams they asked it several times. I bias compensation technique. Let us understand it. How I cancel this current? We'll see. So Pandita here, the current here is zero because this side potential is zero, my friend. This side potential is virtual ground, zero. 0 minus 0 by R1 is 0 or no? Right, both sides potential is 0 volts here. Current kya hota hai? Zero. That is the meaning, Pandit. Why current is 0 through R1? Both sides current is both sides potential is same. 0 0 is coming. That's why current will be 0. That is the reason this current became same in the feedback loop. One of the easiest topics, we'll make it tough actually. Very easy to understand these concepts. So finally, I think this is my problem how to solve in exams. Anybody give bias current with RF resistance, easily I can solve the error how much is coming due to I bias. So let us understand how to cancel this current. We must require a trick for it. Let us make it in the next slide. We call this as I bias current compensation technique. How do we keep this bias current compensation in every op amp? Indirectly in workbooks they kept this technique, but we don't know what is the technique. Today we'll understand what is the technique they apply for op amps. Okay, what is the compensation technique? So let us understand the final technique. So I'm expecting it is completed. Okay, let us move to I bias compensation. Okay, how to do the I bias compensation. I bias compensation, how to start completing this session. Everybody is clear? I'm expecting up to here. Mathematics is also simple to understand. In this class, just you have to understand that I bias can be written as I plus is equal to I minus, according to the background mathematics. Rahman, if output will be 0, we'll wait with compensation technique to get output equal to 0 for what? For errors I'm not telling for your inputs. First error put 0 कर सकते. In future I can give the signals so that it will get amplified well. Okay, at this point output 0 होते ही must be happy because errors 0 कर रहा हूँ ना. If 0 errors if you make it, I can give the signals for amplifiers. If I don't make errors 0, I'll not give my inputs. I'll wait for it. Please make the error 0 first, then I'll do it. That's why first you have to make this error 0 by using some technique in the circuit design. So what is the technique? We'll see. Ashish, थोड़ा wait करो यार. IS0 का last topic. First I bias current we are finding. Okay, I bias होने के बाद we teach IS0. So let us see one special topic today, which we call it as I bias compensation. We say this technique. It's a very beautiful technique. Try to understand it and just experience the technique. In all electronic circuits in op amps, this technique is a common technique. R3 is equal to R1 parallel to RF. There's one new technique I'm using called I bias compensation technique, where in my amplifier I'll introduce one new resistor called R3. The resistor, Arpita, your messages are visible, don't worry. Okay, your messages I'm saying, don't worry. This R3, where to keep in my op amp, you can see. This is your op amp. So minus, we have some current here. I minus, and plus is there. Here, I plus. So we have two currents like this, I minus and I plus. This is your output, V naught. What I'm doing here is, I'm giving one resistor here called non-inverting side, R3, one new resistor here. And here, same R1 will be there for amplifier. There will be some RF. This will be ground. So what is my new technique here is, in every op amp he suggested me, why can't you keep some R3 design here? So that it will take care about your bias compensation, called current bias compensation. Maybe this will take care, he said. So how that R3 will take care? This bias current को कैसे cancel करते हो? Let's understand the mathematics. Suppose if I take this R3 extra, what will happen? In my calculations, what is the difference will come here? Because of this, the same current will go, I plus will be there. But I have seen that the virtual point has been changed. Here V plus point has changed because there is some drop is creating due to error. So this drop we can write it as minus I plus into R3 we can write. This is the error is coming. Previously no R3, we don't have any error, 0 is a ground. But because of this R3 resistor, where your offset current is entering to R3, automatically created a virtual point, that is V plus point has changed to minus of I plus into R3. Because 0 minus this value will come here. So virtual point is changed. The same V plus we have to take here now. So this will become minus I plus into R3. So this will come here. Virtual point will come. So can you see that previously we said no current here, but now the current is flowing here because 0 minus some drop is there. So it will become I plus into R3 by R1 current is going. So these are the differences coming in the R3 effect in your op amps. Up to here it is clear, I'm expecting. Because of R3 we got a drop here V plus. That V plus became V minus, you got some current there. Then what is this current? You will get some current from the op amp. You will get current from the op amp. This current if you want, this is one current, this is one current and this is one current. So let us understand this current will take some letter, some Ix, some current. So if you apply KCL here, KCL at the point of V minus, I'm applying KCL. This one current is going as output I minus current. So Ix plus I plus into R3 by R1 will be equal to I minus. This is the way you can write. Okay? This current plus this current will be equal to I minus, you can write. Let us understand what is Ix now. Ix is equal to I minus I plus into R3 by R1. So I have written like this Ix quantity. But according to our analysis, you said that I bias can be written as simply I plus is equal to I minus is the story we have. So I plus and I minus individually is called I bias according to our mathematics. So here I minus I plus we have two different quantities, but we have made it as I bias current. So Ix can be changed as I bias minus I bias into R3 by R1. So this is called Ix current. So now you can find out what is output voltage seen from here. This drop plus this drop is output voltage. So output voltage can be written as Ix into Rf minus I plus into R3. So this is my output, seeing the board. This drop plus this drop will be the output voltage in the class. So finally I think Ix, whatever you are seeing, Ix can be written as I bias. You just take common 1 minus R3 by R1. Otherwise we'll do it like this. You write I bias minus I bias into R3 by R1. This total term is multiplied by Rf minus I plus into R3. I plus को हम लिख सकते हैं I bias into R3. This is I bias into R3. So like this you can write the concept. Wherever you see I plus I minus, you can write as I bias. So multiply this Rf into this part, it will become I bias into Rf minus I bias into R3 by R1 into Rf minus I bias into R3. Just if you take common now, I bias into R3, I take common. So this becomes I bias into Rf minus I bias into R3. If you take common, it will become 1 plus Rf by R1. So like this you are getting the concept. So what is my interest in the class is, your output has to become 0. The answer 0 per output. So we have a trick here. This R3 you have to design some resistor. In this final expression, R3 you design something where the second quantity and first quantity should come same. That is a trick called as bias compensation. You try to keep RE whatever you like, but that has to come the shape in such a manner it should be equal to I bias into Rf. Then he suggested me the trick here. Why can't you take this R3 as R1 parallel to Rf? If you take R1 parallel to Rf, what will happen? I bias into Rf minus I bias into I bias into I bias into R3, you can write it as R1 Rf divided by R1 plus Rf, which is a parallel combination of R1 parallel Rf I have written. R1 Rf by R1 plus Rf into side by we have R1 plus Rf divided by R1. Can you see that this quantity will get cancelled and this quantity will get cancelled? So finally you got I bias into Rf minus I bias into Rf. The answer became 0. So this is the story how I can make offset voltage V0 0. I can do it by the trick called as R3. In the exam they'll ask you, please calculate R3. At that time your formula should be R1 parallel to Rf. If you can design the circuit like that, automatically your offset will become 0 because of bias current compensation technique. Okay? In every op amp who will keep R3, you feel that there is a bias compensation is going on, or offset current compensation is going on. In most of the questions they'll keep R3. You think that's why R3 he kept. R3 has some importance that it will compensate your internal currents. Okay, it will compensate your internal errors. But that R3 when you go for external circuit, we are making short because I plus will be 0. We are assuming and we are doing the problems. But inside currents will be compensated by this R3 concept. That's why in previous class when I'm teaching differential amplifiers, have you observed or not? I kept the R3 resistor there. So student will think, sir, why he kept R3? There is some reason for R3 is it will compensate the bias currents. Automatically bias currents go neglect karega. So that is the beautiness. Why in every op amp design, if you keep some R3, what the advantage is? This is my advantage. Okay, R3 is a resistor which can compensate the offset current called bias current in electronics. So this completes the story, how it came, the like concept. So finally the trick here is, the trick you have to remember is, R3 is always equals to, I'm writing like a big formula, it is R1 parallel to Rf. This technique is called as I bias compensation. This technique is called I bias compensation in our electronics. So if you complete this, last topic is remaining, that is called as final topic, that is called IS0 compensation, last technique. So by 10 o'clock, I'll give a break for you. So 10:30, we'll start the 2 more topics remaining, that is called sleeve rate, and one more we have is that gain bandwidth product. That also will complete. After that, we'll try to start doing the problems. Okay? So complete each and every topic I'm covering, so you'll get maximum benefited in the practice of analog electronics. Each and every topic I'm covering, so it will be very happy for you to practice in easy manner. Pandit is asking I bias, A0, all are due to DC voltage mismatch. Yes. Pandit, 100% your statement is correct. Pandit, you said what you said is 100%. That only board may be bata, no? It is not due to my signal conditions we got the offsets. Offset is a board come from DC. DC imperfections they'll say. Okay, mismatchings due to DC environment, we got these errors. Okay, always remember this simple thing. How V plus and V minus are same. And inverting current. Rahman, I said one important step for you in the class is when you are solving one error, the other error should be 0. You have to take in the class. If V is 0 is equal to 0, suppose you have taken, okay, assumption, then V plus minus V minus is 0, then you can consider V plus is equal to V minus, I plus is equal to I minus, then you can start I bias calculations. So whenever you do one thing, other things has to be taken as a condition as 0. So that knowledge you have to apply from the board. So in this class what happened, then I plus I minus same हो गया, because I is 0 को 0 assume किया. That is the main reason. I bias current also became I plus is equal to I minus. R1 and RF, how it is parallel? What is the meaning here? और क्वेश्चन क्या बात कर रहे हैं आप? ये दोनों पैरेलल नहीं है. इधर R3 we have suggested a resistor that should be a combination of R1 parallel to RF. We have to take that I suggested. Not saying that these two are parallel here. The structure is not parallel. We have taken a condition that the resultant two resistor parallel combination that I keep it R3 as suggested. So you're asking me the question how it is parallel. What is that question? Shamita, I hope you understood. What is the type of questions you'll get here? Always. R1 and RF, how it is parallel is not a question here. R1 और RF को parallel हम लिया such that this quantity will get I bias into RF. So ये पूरा quantity 0 करने के लिए मैं लिया condition. Okay? और condition लेकर आंसर को 0 कर दिया. These are the things how they'll apply the subject. So let us come to the final 10 minutes classes, the 10-15 minutes. The last point I'll cover and I'll stop here. After the break, we'll continue with sleeve rate and final one in the class. Okay? So let us cover the final issue. Keep the heading. Keep the heading. Last one, case 3 analysis. Case 3 analysis. Case 3 analysis. The last point here is that the offset will be completed today. This only has taken one more class, offset. The last one. Keep the heading, case 3. Case 3 is offset current, how to calculate error. So always remember, first you have to compensate the bias current, then you have to talk about offset current. Because offset current is smaller, bias current is more. So bias current already I made 0 in the class now. Okay. Now how I can finish this last error, the final error, which is I0. So case 3 you can keep heading. Last problem. Case 3. V0 offset due to I0. So whenever you want to make a V0 offset due to I0, the condition here is VI0, you have to make it 0, and I bias should be 0. Now I bias to make 0, what is the technique we have is? The technique is R3 compensation is there. Just we'll apply R3 compensation. So directly I bias will become 0 now. But what is actually R3 here is? It is a combination of R1 parallel to RF we said. But we know that the range of R1 will be 1K to 10K generally, this is the range. Your RF range is 100K to 1 megohm I said. So that means shunt resistors, series resistors are not having same ranges. That means RF is much greater than R1 technically. When RF is much greater than R1, your R3 can be approximated to R1. So this is your concept. So no one would R3, you can write R1 in the classes because R1 is a low resistance, RF is a high resistance. High resistance parallel to low resistance will be low resistance. So I change this answer. In place of writing combination, I write technically the answer is R1 because of these technical issues. RF is always 10 times more than R1 we take in our classes to get the minimum gain as 10. At least 10 is the minimum gain you must get in your closed loop systems. So R3 should be equal to R1. If R3 is R1, then you can see in the board your design. Minus side we have I minus, we have I plus. Here we keep some R1 to ground. Here we keep R1 to ground. Here we keep RF to output. So correctly if you observe, in the last topic what happened is your R3 is R1 in the class. Okay, in place of writing R1 parallel to RF, technically we can write this R1 because RF is always 10 times more than R1 to get the gain in negative feedback systems. So if you know this trick, can I say that the current going here is I plus I can take, so that here we get minus I plus into R1, same way we are doing. This answer will become minus I plus into R1, but this current will be 0 minus, so this becomes I plus. So correctly observe the concept. When you take these two resistors are same and we have the same potential, the currents will go same. So other side also we got I plus now in the class. Because of R3 became R1, so I plus current is going in both the branches. Here also I plus, here also I plus. Now what is this IX current here is? This IX, by KCL if you apply, IX plus I plus will be equal to I minus. By applying a KCL at V minus. I just applied the KCL, I plus plus I, IX plus I plus is equal to I minus. So what is IX? Is I minus minus I plus. So this is about your IX value in the class. So in magnitude, if you want to take this, in magnitude, if you take this, you can write as I plus minus I minus. In magnitude you can write. You can alter I minus to I plus to I minus if it is in magnitude sign. So finally, we can write this as simply I0 in the class. So the difference is nothing but I0. So that means this current, whatever you are seeing, we can write this as I0. Okay. So what is V0 answer? Is Ix into RF, this drop plus this drop, minus I plus into R1. Like this we are getting. So this drop is I0 into RF minus I plus into R1. So if you see in the formula, this error is coming due to RF resistance and this error is coming due to R1. As we said, RF is much greater than R1. I think I plus R1 is neglected in the drop. I plus R1 you can neglect. That error will be very small in value. So finally your answer, V out offset will be equal to I0 into RF. So what is the beautiness of this formula as you can see? Why this formulas are easier for me to finish the offset calculations is the previous similar answer we got. I bias into RF current wise. Here I0 into RF. Always current errors will come with a multiplication of feedback resistance. So the formulas are very easy and comfortable to recollect in exams. So this is the overview of complete package of offset calculations. Now, any question you see in Gatebooks, every question you'll answer with this notes, whatever I have given for you in the class. Okay? So sometimes they'll ask you, PA0 error, we know the formula. Offset calculations. So this is the time for us to take break. 10:30 will start. 1 hour we'll spend the time for remaining two topics. One is sleeve rate calculations and one more is offset. Sorry, one more is gain bandwidth questions. How to do it? If we complete these two parts, slowly I'll enter into the what to practice. So let us complete this. So mic is not off, so power is off. That's why maybe you're not listening. Just give me a time for it. Just power fluctuation came here. That's why you're not listening. Now you listen. Try to say. So mic is not off, my friend. Power is off. That's why again power came. Now it will come. Just wait. Just copy up to here. Just copy up to here. We'll take a break up to 10:30. Break. Up to 10:30 you can take a break. So 10:30 we'll finish the remaining two topics. That is sleeve rate, one topic,